Hello, everybody. I'm Cédric Villema. I'm the president of DataBene, which is a French company providing PostgreSQL expertise worldwide. And today I have a date with my FC, and I believe you have a date with my FC too, because you're attending and watching this nice talk that I expect to be nice. Um, I believe it will be important for you if you are interested by PostgreSQL performances, by PostgreSQL observability, and better understand how this bit is working in the background. So please keep watching. Here we are. This is the day for my appointment with the psy. And so let's go dive in and see what he has to say. Well, I'm Cedric Villemain. I'm employed for the scale field for maybe nearly 20 years already. I started with full text engine into PostgreSQL. It was very interesting. And then I grew up managing and starting a PostgreSQL expertise companies for the last 15 years. Currently, I'm running Database, and we are a PostgreSQL dedicated company. We are not software editor. We're providing fully open source support and research program and training center. And so the point of the talk today really is, did you ever ask yourself, how can I manage that? I have a vacuum folder, I have a heavy task to run here right now, but at the same time, this is a production machine, and I will pop up another terminal with a top so I can monitor what I'm doing. And if there is something wrong, I can see that on the top, and then I can act on my vacuum folder or my heavy task. Maybe this is just a huge SQL query which is saturating the IO, whatever. I have one eye on my command, one eye on my monitoring. And then we are looking today, right now, at solutions so you do not have to look at 2 points at the same moment, because we provide you with solutions to be able to observe this monitoring and also to take action, to be active as the pressure on system is growing. So the agenda is to discuss three main top points. First one is PostgreSQL requirement and processes. And another is about PSI, process state information, what it is, where it's coming from. And then we look shortly into PGPSI, PostgreSQL extension, and look at some few items in this field for the future. So PostgreSQL processes, uh, there are around 15 processes in PostgreSQL which are interesting to look at. And I classify them in distinct categories. So here we have a distinct group which I define as critical. So here I put, and this is my arbitrary decision. You can do whatever you want on your own. The Postgres process. This is the main mother of PostgreSQL process. So this is very subject to latency, and we want to really protect this process as much as possible. This is critical piece. And then we have other processes which are very important too. Auto vacuum, slot sync workers, WAR receivers, WAR senders, WAR writer, and we have then other kind of activity on the process, on server. You are connecting to PostgreSQL with a regular backend executing SQL command, but also maybe you have some background worker which are started and doing some tasks for you in the background. And then I define another group, which is maintenance process. So auto vacuum workers, background writers, checkpointers, WAR archiver, and summarizer. Summarizer is pretty new, but all of them are important too, and checkpointer is pretty important. But after all, it's not really disturbing the server, except by imposing some performance bottleneck. And then we have auxiliary process like the logger and the fresh new thing from PostgreSQL 18 I workers, which I was absolutely unsure where to put it yet, because to be honest, I didn't dive into the IO workers really yet. And it, depending on the configuration, it may go into the maintenance, or it may go into the critical, or it may go into the workload process, depending if it's really, I don't know. This is another point to explore, and maybe you will be happy to explore IO workers with PSI later today. And those process, so we want to categorize them. The purpose here is to be aware there are several kinds of process, and we want to know is to understand how they behave, what they need. And so for PostgreSQL, there are three main important topics as usual: CPU, IO, and memory. But what's important to note is that PostgreSQL is a fork process model. It means that when you look at a process on your machine, PID, process ID, this is a single process. There is no thread in PostgreSQL, so it's going to run only a single action at once. there is no parallelism at this point. So for monitoring and observability, it makes things a lot much easier. On CPU, we have workload where it's very compute intensive. Maybe it's because you create an index, but maybe just because you're running analytical workload. In such situation, you want a fast and efficient CPU unit. At the opposite, you may be running just transactional workload, whereas a lot of OLTP, very quick transaction for maybe a web application. And then you will probably want a lot of cores and a lot of CPU. More important than just getting fast CPU unit. Those are distinct workloads. We want to learn them and to understand them and to be able to observe them. There is the I/O, and on the I/O, we have one very important part in PostgreSQL, which is a write-ahead log. You probably heard about it. This is a critical journal. We want it to be always available to write synchronously to the disk. So this is a single process which is writing to the whole stream and as to the WAR file. And so we want to ensure that it always got resources. And then we have a lot of other activities which is managed by backend, by I/O workers, or also by background workers, checkpoint workers, and so on, which are going to read and write on indexes and tables distributing I/O among distinct processes. And last point, we have the memory. In PostgreSQL, this is very simple. We have at the beginning pre-allocated shared memory by PostgreSQL. When it starts, it allocates some shared memory and will keep using it during its work. Be aware that PostgreSQL supports huge pages, and it's very interesting to activate huge pages. And it's really always a win. And then we have dynamic shared memory allocation. Means that after PostgreSQL started, it may request again more shared memory to manage some workload and to share information between backends, for example. And then last point, we have a per process local memory. So it means that we have distinct kind of access to the memory. Some is shared, some is private. And so we want to know also what distinct processes are doing to PostgreSQL and how they use CPU, I/O, and memory. We need to make a map of that. And this is precisely what we want. We want to be able to observe all those processes, understand their workload, and so we can define what kind of resource we need and what are the bottleneck we want to protect from. And here, start to be interesting to look at the PSI, precious data information. This is really a way to, instead of be notifying too late that things are going bad, you can be informed or you can look at the metrics a very short term to be aware of what is running and what's happening on your server. Okay. And so it allows us to provide very precise and quick reaction and adjusting workload. Maybe you're going to throttle some process or you're going to pause or kill some queries or whatever you want to do. It has been introduced 7 years ago by Facebook. And so it's present in the Linux kernel since 2018. Here you have a link with a QR code. There will be other links later. So if you want to get them at the same time, maybe you want to snap and get a QR code as we go through them. So PSI, persistent information, is used by major people, I would say. Facebook, we initiated this project and we have pushed the first pages to the Linux kernel. Is a great and large user pattern of PSI, where they do most of their management apparently with PSI internally, optimizing resource usage and processing. And then there were all the patches provided by Google in order to get not only the metrics, but also event notification, which is a key point because then we can get metrics. And if it goes over some threshold or limits, we can get a notification that something is happening. And they use that to be able to provide on Android a light daemon, which is able to manage the memory on the Android device using the precious data information. Another major user, Cloudflare. Cloudflare has wrote and is proposing a PSI exporter for Prometheus. So it's very convenient and also probably interesting to note that if those major people are using PSI, there is probably an interest to look at it more seriously. Oh, so what's interesting, this is easy. Very often on Linux, you just have to look at files. You send some message to a file or you just cut a file, meaning you're going to read this content, and boom, you get this information. And here we have three files, /proc/precious/io or CPU, or memory that you can look at, and are going to be always the same. Two lines with sum and full lines with average and totals. Okay. And what is interesting is in these two lines, we have a sum, and sum means that some process, maybe not always the same, but some process is stalled. At some point, he's stalled on a resource. It means that he has to wait and cannot do anything. He's waiting for IO, he's waiting for CPU, or he's waiting for memory, depending what procedure you're looking at. And there is a full line. The full line means all the active process are stalled. So this is a real problem, very probably because your server is not doing anything, just waiting at this point for everyone at the same time. Something probably you want to avoid. And there is the average. So the average is for 10, 60, and 300 seconds to be notified, to be informed about the percentage of time you have been installed during this period of 10, 60, or 300 seconds. And last point, very interesting, the metrics. Beginning are just average produced by system, by the kernel. But here you're going to increase and get increased by microseconds on this total, allowing you to provide your own average. You maybe want to provide an average on 20 seconds or in 500 seconds, up to you. You want to detect spikes, bursts, or whatever in the start procedure, it's also available because you have these microsecond metrics which accumulate every time. You may notice here a point about the average. This is something common. You use it already, maybe in your life on IT. But here with the PSI, this is a little bit distinct because it's not the same average that you use to get for the load. Load average on the system is based on number of CPU. With PSI, this is just a percentage of time which has been spent waiting for something. And it's completely unrelated with number of CPU. So this is a very easy metrics to consider. There is another interesting point which makes it distinct from load average. In load average, you have a 1 minute window and you sample each 5 seconds. With PSI, you have a window which is from 500 milliseconds to 10 seconds, and you have a sample each 50 milliseconds. It means that clearly you can have much faster reaction and much fine-tuned observability on your system. One constraint at the moment is that non-root users are limited and they cannot use a window. They must define a window of 2 seconds or a multiple of 2 seconds. This is a barrier in order to not over-consume the kernel on those PSI information. And the last point about average is that on load average, you have an overall load, whatever the process are doing, more or less. This is very fuzzy. Here with PSI, we have a very clear distinction between CPU, IO, and memory, and some processing which were accounted for CPU with load average are clearly separated between CPU and memory with PSI, for example. So it's much it's more accurate. I believe to get to understand PSI, one thing is to do a demo, but for a webinar, it's not always easy and there is failure possible. So I just prepare you a pseudo demo, which is this slide where we have two tasks, A and B, starting to run on a server. And then after 2 seconds, they are still running. And it's very nice because they're just running without being stalled at all. But then at the 2 seconds, task A start to be stalled and is waiting on something, depending what you are looking at. Maybe you're looking at CPU or IO. Let's say we are waiting on IO for 1 second. And so this information about this process is going to change the average and change the total. So we can see the total. And here I put seconds instead of microseconds because it's easier to read. So you can see that we are waiting for 33% and we already accumulated 1 second of stall time. And then it keep on running. And the second task, task B, start to be stalled also. So at this point in time, we have some counter which is going to grow because we still have some task which is stalled, but also at the same time, all tasks are stalled. So the full line start to increase. And so we have a very clear information. If it's just one single process, it's stalled, maybe it's not so critical, but if all are stalled, there is probably something going on. Later, the task A get back to work and task B remains stalled. And so you see that the counter for the sum will be accounting the time spent by task A then by task B being stalled for something. And you see on the bottom that the average and the total have been moving. And as we go over 10 seconds, over 10 seconds, we get 60% wait time on some process, and we get 40% wait time full on all processing, 4 seconds and 6 seconds. So this is clearly what we want to have, and a very tiny level with PSI, getting those metrics, and even more getting some feedback when it goes over some threshold. So here we have that. Today, with PSI, we're able to observe very precisely how the system is behaving and how the pressure is growing. We have that at microsecond counters, and we have very frequent samples of 50 milliseconds. This is superior to any previous solution to be able to monitor and to observe a Linux machine. The other big angle of PSI is this event notification. Clearly, here we are able to define triggers, meaning that we're going to say to the kernel, I am interested to look at the I/O or memory or both of them, and I want to be informed if some task is locked on I/O for that many seconds over that many, for that many milliseconds over that window of 2, 4 seconds or 6 seconds. So let's take an example here where I register a trigger, which is to be fired once we have accumulated more than 250 milliseconds of start time on I/O over 4 seconds. Okay? So we just send this text message to the file, not with a Linux machine. You need to have a code for that. And if we go over this threshold, we get an event. What we do is that then we define the trigger, we poll on the resource on the proc IO, and if there is something to be signaled, kernel will send us a PRE signal, which let us know, oh, something with priority and interest is happening on a pressure IO, meaning your trigger has fired. You are under pressure. And you see, this is very low level API. You can use it to monitor, but if you want to do polling, you probably want to use existing tooling or what your own tooling, or you do that with your own code. Another point is the side of the PSI is that PSI is not only available for the global system, it's available for each C group on the machine. It means that for each C group, we're able to get the average load on CPU, IO, and memory, and be able to compare process with other processes in the same C group. For example, in C group, if we say all tasks are locked, this is all tasks from the C group, not from the system. Be aware that C group are used everywhere today. This is base for systemd, which is running Linux boxes worldwide. And this is used by Docker, this is used by Kubernetes, this is used by mostly everything is running on C group. So here with PSI, we have a very fine information even in your container application. So what it brings so far, this PSI is a more granular metrics. It's an easy to use user interface to observe and adjust the workload and to get kernel event notification. This is very convenient. We have external tooling as, for example, this PSI exporter from Coolfare, and there are many other tools available in the monitoring field. But for PostgreSQL, I wanted to get something available for us, DBA, to be able to operate and to get to know more easily our workload and what's happening on the PostgreSQL instance. So I bring in PSI to PostgreSQL with PGPSI. So this is very similar to what we thought. We're going to register triggers with a C group. For example, here I'm interested to look at the workload C group, and I want to control the resource IO. And if some task is stalled for 50 milliseconds over the last 2 seconds, I want to be informed. And here you see the file path, which is shortened, but it's a file path on the system that you can also go and look and do a cat on it, so you get information directly from IO pressure on this workload C group. Once you did that, you have two solutions with PGPSI. One way is to just use interactive polling. So you just start your session, you register triggers, and then you execute PGPSI poll. And then if events are fired, you get a notification informing you, for example, here that we have to wait 50 milliseconds for 50 milliseconds over the last 2 seconds, and we got some IO pressure in the group workload. The other way to use it is to use it as a background worker, meaning that you are going to run this background full or this huge task, and you want it to be suspended or canceled as soon as the workload on the machine is going too high. So one way is to just register triggers, which are accurate. Maybe it's going to be a sum of I/O, memory, CPU, and you want to control these 10 kind of things. And if they fire one or the other, then it's going to suspend the task which is running on. This background worker is dedicated to my session. It's not working for all the processes, just for my session that I started, where I started the background worker. Then I start a vacuum full, and after some time, because I'm running a PG benchmark at the same time, vacuum full is cancelled by my background worker, and so the PG benchmark can keep running. If you're interested by the PGPSI project, I invite you to go and look at the website. So it's hosted on Kohlberg. Kohlberg is a non-profit organization based in Germany, which is providing a lot of open source support. The project itself is under PostgreSQL license, and so we will be very happy to have you join our community and be involved in this project. Feature of PSI is feature of PSI is on two angles. We have first an ongoing discussion on the kernel side. We want to get shorter window for PSI. As I mentioned, when you're not root, you have 2 seconds only. You can do 2, 4, 6 seconds. But often we want to react more promptly after maybe 500 milliseconds or 1 second. This is very better to be able to adjust the workload sooner. Okay. The other point is that there is ongoing discussion to get PSI support in eBPF. So I'm a little bit excited here because eBPF is a sandbox engine inside the Linux kernel, which allows you to run efficient program to manage what's going on in and out. And so it's a good place to insert things and to change what's happening. And so getting the PSI API inside eBPF allows us to provide sandboxed software to do memory management in place of, for example, the OOM killer from Linux. Another angle is the future of PGPSI, and here I have two things I want to do. First thing is to provide a pluggable trigger action. So the point is that monitoring and taking decision into this field is very complex. It's hard to get one algorithm for everything. We tried for several decades and it's always complex. So here I want to provide just the basic, always interesting features like cancel this query, but also allowing you to implement your own logic and define your own action on triggers. So PGPSI purpose is to provide you an interface so you can add and implement your own logic based on your own workload. The other angle is to provide stat interface for PGPSI, thus providing an option to export metrics from the C group we define here and to observe, assess, and adjust our workload also on PostgreSQL itself, but also by exporting them for any monitoring system. As we saw before, you can also just use a PSC exporter from Prometheus. PGPSI is not very important for that purpose, but when you're a DBA, you like to be able to connect to PSQL and get to know about the system as you're connected under SQL and not having to go to SSH and execute top command or whatever. This is what it brings. With the stat, we expect to be able to know how many times a trigger has been fired, for example, or whatever other information is interesting. I wanted to do a small demo, but honestly, it's not very convenient. So instead, I just get 2 screenshots just to make a difference between what we had and what we can have today. The first thing here is the top. So here I'm running a PG benchmark. It's loading my machine. And you see there is commit and there is updates and there is IO workers. We can see them and checkpointer, background writer. All of them are visible on the top. And you have interesting information. You have a load average. All of that is nice. Okay. What I'm bringing here with PGPSI is more vision where you can know for PostgreSQL itself where it's happening and what's happening. So here it's much easier for me at least to see, okay, on my workload group, and my workload group are my background worker and my SQL queries. As I'm running my PG benchmark, I can see there is a lot of stall time. I'm waiting nearly 2 seconds, over 2 seconds. So I am very stalled on IO and on CPU, as is visible on the top 2 first row. And I can also see that there were some stall time on a wall writer, 1 millisecond, which is not good. We know that already. Oh, and apparently the background writer and the wall writer were active on CPU at the bottom. So this is much more detailed. I expect this kind of information will allow us really to understand better how PostgreSQL processing are um, behaving, what resources they need, and to ensure that we can have smoother production workload. So it has been a quick introduction to this topic. I hope you like it. And then I have this slide with some, I believe, interesting links to look at the work ongoing for PSI into BPF, which is the first link. The original PSI documentation from Facebook Microsit, which is very easy and nice to read, a good overview, and go into the technical details of what they did and why, because they changed the strategy over time. And then the official kernel documentation and the properties exporter from Cloudflare. So here we are. I hope you like this talk, and I'm really happy now to listen to your question or comments and to feedback to you.